So let's start. So hi everybody. My name is Cooper Madroni. I graduated last year from Queen's Engineering. I can see some familiar names and faces on this call, so it's great to be back, and it's great to be giving back by doing this presentation. So my presentation is titled Quantum Machine Learning, and I can't imagine any of the other presentations had as many buzzwords to work with as I do. But how I really want you to think about this presentation is not quantum machine learning as a single concept, but actually the intersection of quantum computing and machine learning as two separate and interesting fields. So how this presentation is structured is I first want to give you an understanding of quantum computing. And I want to tell you how we use quantum computers to perform the task of machine learning. And I would say I have three main goals for this presentation. The first one is to inspire you guys about this field. Now, I hope at least some of you find this really exciting. And by bringing awareness to this topic, you might consider careers or side projects, or even your QMind projects to do something in the space of QML. And the second one is I want you to see past the hype. Part of the challenge in the early days of QMind was actually that machine learning seemed like this mystical dark art at the time. And you had to actually remove that mysticism to treat it like a field that can be learned and practiced. And so that's what I want to do for quantum computing and quantum machine learning. And the final goal for this presentation is to kind of act as a launch pad for your own exploration into quantum computing or quantum machine learning. And so after I pull back this curtain, I hope you kind of do some more learning on your own. As a disclaimer, I'm not an expert in this field. I have only done one internship in this, but this has been obviously, it might put me ahead of most people, I imagine. But anything I say, don't take it as gospel truth. Just remember, we're all just trying to learn, and we're definitely just trying to share some knowledge. So first, who the heck am I, and why am I giving this presentation? Like I said, I graduated just this past year, which makes my first year of engineering in 2016. I did applied math and computer engineering. And while I was at Queens, I did a ton of clubs. Between the first and second year, I probably did like 5 or 6 clubs. And somehow at the end of all that, I still felt like I didn't really have a direction. And most importantly, I didn't feel like I had a skill set that I could market myself off of. Like I felt like I was so unemployable, even after all these groups. And at the time, you were more likely to hear machine learning in a pop science news article than you were on campus. But out of this frustration of my lack of employability, that actually gave me the direction to start QMind. And at the time, none of us really knew anything. No one really on campus was an expert in machine learning, and me and the friends that were the very beginning team were just willing to give it a shot. And obviously, a lot of great stuff has come out of that. But for me personally, I got my first internship just because of my association with QMind. The industry is really hungry for talent in AI. And it was actually in that internship that I learned how to code. I didn't know how to code when I started QMind. And one of the things that I want to get across is, there are always barriers to knowledge, but on the other side of those barriers are really great skills, really great opportunities. And I want everyone to kind of pursue those. So in my third year, QMind grew. We launched the conference, which you guys might have heard about, Kukai. And then that summer, I did a quantum internship at a company called Intractable Labs in Singapore. And I might have, for those who are on the call, I mentioned that post-graduating, I was working on a startup as part of something called the Next 36 program. It was an AI startup. I got to work with GANs and did a bunch of generative ML. And then we wound the startup down. And so my full-time job is actually going to be working at Microsoft, and I'm going to be flying to Seattle in 7 days. So wish me luck. And here is a nice fun photo. This is the very first QMind team. There's a lot of people missing, myself included. But if you can imagine, QMind once was just this. And it always blows my mind to look back and see just how much it's grown. But let's talk about quantum computing. So it's my hope to first show you why quantum machine learning, or QML, is important in the first place. Why do we even need it if machine learning is everything we hope it is? And the best place to start is actually by giving you all a sufficient understanding of quantum computing. This photo is probably what you all imagine when you think of quantum computers. This is the so-called golden chandelier. This is actually only one type of quantum computer. This is the type that IBM and Microsoft have, but a lot of other companies are doing it in a lot of different ways. And that's one of the exciting parts about this field, is that we don't actually have a dedicated hardware. There's a lot of ways you can do quantum computing. They all have different benefits. So we can draw a really interesting comparison to where quantum computers are today and where the very first computers were in the early 1940s. Quantum computers are big, they don't have that much memory or compute power, and we don't really understand how to use them to their fullest extent. Something fascinating I learned is that most of the algorithms that we use on our computers today for searching or sorting, they weren't found theoretically. They weren't found because someone sat down and proved the math. They were found because when computers had enough power for people to play around with, they actually discovered more efficient algorithms. So quantum computers are definitely limited by their capacity now, but when they really get going will be when we can play with them and experiment with new projects and ideas. Another great comparison, the photo on the right is a 5 megabyte hard drive in 1956. Like, I just think that is nuts. And so if you can imagine and project forward where we might be in decades, that's a really exciting idea to me. So let's start by saying, what is a quantum computer? And let's assume that you have kind of a baseline knowledge of normal computers, and we'll extend that to quantum computers. So the computers that you use are actually called classical computers, and that's because they obey classical mechanics. And at a fundamental level, all your computers rely on storing information as bits, which is the basic unit of computing. A bit can be a 0 or a 1, and when we compute, what we're actually doing are putting those bits through what are called logic gates, operations like and, not, or, and these logic gates are actually allowing us to simulate operations like addition and subtraction. So we use these gates to do something far more, complex for a computer at least, which is addition, subtraction, multiplication, division, and many more things. And that's it. All your computer is doing are moving and storing bits and putting them through gates like this. But just like classical computers, quantum computers have their own set of gates, and this is actually just a small fraction of them. But while these gates can simulate addition and division, they can also perform quantum effects that a classical computer cannot. And these are the extra special quantum operations that are superposition, entanglement, and interference. So let's talk about what advantage this gives quantum computers. We're all familiar with classical bits, and they can be in a state of 0 or 1, and that's because a bit is measured by trapping electrons in a transistor. When the transistor is full of electrons, we say it's in a high state, or 1. And when it's empty, we say it's in the low state, or 0. Now, qubits are objects so much smaller than transistors that they are affected by quantum mechanics. And when objects are this small, we can't actually say with certainty whether it's in a 0 or 1 state. Instead, we say that there's a probability of 0 or 1. So this spinning coin, which we'll say is our qubit, has a 50% chance of being in the 0 or 1 state. And when it's in this state, which we call superposition, it is not both 0 or 1, and it is not secretly in 0 or secretly in 1 without us knowing. It is actually encoding a probability of either being in 0 or 1. And it's important to note that when we measure a qubit, like you can imagine, we want to look inside the box and actually see if it's 0 or 1, it collapses to either 0 or 1, and it loses this kind of magic probabilistic property. So what's important is that our quantum gates are operating on probabilities. And that's where we get this advantage, which I'll explain more. So let's say we have control over 4 bits. What you see here are all 16 possible states of 4 bits. But if you have 4 bits, you can actually only act in one of these possible states. You can only be 4 zeros, or you can be 4 ones. You can't be both. And so our 4 bits can only be one out of the 16 states, or more generally, n bits can only be one out of 2 to the n states. Now, if we go over to qubits, because these qubits exist in a probability of states, when we perform operations on them, These qubits are, in a sense, in all possible states. Now, if at this point I've lost some of you, the only main takeaway that I think you should have is that these qubits give us more representational power. We can do more with qubits than we can with just bits. So here's a motivation of why we need quantum computing. This is the caffeine molecule, and as far as molecules go, it's really not that interesting, and it's fairly simple. But still, if we wanted to simulate a caffeine molecule, it would take 10 to the 48 bits of information. That is a trillion bits. That is crazy. But there are a lot of reasons you'd want to simulate caffeine. For instance, you might want to perform tests to see how it reacts with other drugs, or you might even want to test on it without having to use live subjects. Now, this seems like a great idea, but until you realize that there are 10 to the 49 to 10 to the 50 atoms on Earth, we could never simulate caffeine unless we increase the representational power of our basic unit of computation, and that's the qubit. The real kicker is that caffeine isn't even that interesting. If we want to simulate new materials or find drugs that can cure diseases, we're talking about molecules that are dozens of times more complex than caffeine. Another quantum benefit is that quantum computers solve what are known as intractable problems. These are certain types of problems which classical computers are so bad at solving that it takes literally years for them to finish. But operations like superposition and entanglement give us exponential speed boosts to solve these problems. In October of 2019, Google broke ground when they performed an operation on a quantum computer in 2.5 days. But that same operation on one of the world's largest supercomputers would take over 10,000 years. Quantum computers are able to solve problems that classical computers just can't. And as you can see by the caffeine example, these problems are important. We want to solve these diseases. One catch is that only certain types of problems actually have quantum advantages. These problems are typically graph optimization problems, so thinking about doing operations over a social network, or combinatorial problems where every time you add a new person to the network, the number of relationships to consider grows like a factorial. And these problems are everywhere. They're in logistics and supply chain management, drug simulation and discovery. The famous example is that quantum computers can actually break encryption, and even in financial markets. If you were to sell a stock, someone on the other end is buying that stock. So you have this combinatorial problem of matching buyers and sellers. And of course, the topic that we're actually here to learn about is another application, which is quantum machine learning. And I want to convince you to see QML as merely the areas where machine learning and quantum computing intersect. In fact, the basics of these two fields, if you understand them, will get you most of the way towards understanding QML. And so this is what I want you to think of it. These two fields exist separately, but in their intersection is quantum machine learning. And that's why I really think this presentation is quantum computing and machine learning, how these two things work together. So let's build a simple definition of supervised machine learning. In machine learning, you're going to choose a model or an algorithm, and you're familiar with different types of models like convolutional nets, LSTMs, random forest. And within every model, you have parameters which define the model, and these are your weights and biases. Your goal is obviously to find the best parameters for your model by testing it on training data and evaluating it with an objective function, which kind of defines how good your outcome is. So in the end, the main output of this process is a set of optimized parameters that you can use to predict on unseen problems, although it's obviously never as easy as I just explained it. So in this simple diagram of a neural network that you've seen 100 times, we use this to represent the real math that's going on underneath the hood. And this is just a bunch of matrix multiplication. These are the weights and biases multiplied by each other, which determine the output. So what determines the math are the model, the types of layers, the number of nodes, and within these matrices are parameter values. And these are the weights, the biases, and the activation parameters. And that's all there is to a neural net. And so before I show you what a quantum neural net looks like, I want you to remember that you've actually never seen a diagram for this. And imagine the confusion you had when you first saw the neural net diagram. Maybe for some of you that was today, but keep in mind that when you're confused, this is the quantum equivalent, because this is the first time you're likely seeing this. So this is what's known as a quantum circuit. On the left side, you have qubits, and throughout the qubits, moving from left to right, you have our gate operations that I mentioned before. And what do these operations represent? These operations are just a bunch of matrix multiplication. And so just like you guys have learned machine learning, you can also learn quantum machine learning, and you should think of it just like matrix multiplication. And so when you think about QML, think of the model as the order and type of gates, and you should think of the parameters as the numbers that control the manipulation of these qubits. So for instance, with any one of these operations, we can put in a parameter just like we could put in the parameters for our weights and biases. And so how does quantum machine learning work? We're all familiar with how to train a normal machine learning model. Well, we actually take a tag team approach between a quantum computer and a classical computer. We're using the best of each device. The quantum computer is going to give us these quantum programs that have these advantages, these exponential boosts in speed. And they're going to output some number that the classical program or the classical computer uses to update the weights. And they work in tandem until they reach a stopping criteria, just like you might in training, if you've reached a certain level of accuracy or you've reached just a number of iterations. And so now what you just saw is a process that applies to all of quantum machine learning. And so how is this quantum model different? We're going to use the quantum circuit that we saw to put into a quantum computer and feed data and objective function into the classical computer for it to evaluate how good the quantum circuit did. And what we're updating are parameters. So this is just like a quantum machine, just like normal machine learning. The model has parameters. The model has an architecture that is defined by a quantum circuit, and we use data and the objective function to test it. And so really, I think that's as deep as we can go into quantum machine learning. And now I want to talk about the broader quantum computing market. There's a lot of interesting work going on, and Toronto is actually one of the best places to be in the world for quantum computing, or Canada in general. Some companies you might have heard of, D-Wave is a company in Vancouver. Xanadu is based in Toronto. So if you're interested in these fields, you might think, just like what it took to get my very first data science internship, all you need is a project. They're starving for talent. And if you can come to them with an understanding and some small projects done, that'll put you leagues ahead of anyone who is even considering getting to this field. And just like I said, there's a lot of different ways to do quantum computing. You can do quantum computing by trapping qubits as single atoms. You can use photons. So there's an interesting hardware side that is actually much more fascinating than there is in computers, where we all know that we're just going to use a transistor. So how could you get started? My recommendation is, first, I want you to learn the concepts. I want you to watch YouTube videos. I want you to read science articles and listen to podcasts, because it's a whole new world with a whole new language that you might not understand. And then I want you to apply the concepts. There are open source libraries out there, just like there are for machine learning. They're just a little bit more novice because it's an earlier field. But companies like IBM and Qiskit is Microsoft's own platform. They've actually put their quantum computers on the cloud for you to use for free. And there's a really amazing quantum machine learning course on edX. So that is probably, it's very mathematical, but I would definitely say it's a good start. And, read some papers. People who are really great at machine learning, they're not afraid to go on archive. They're not afraid to get to a research paper. And so that's kind of what it takes. And so other than that, these final words, I'd love for you guys to ask me about, I mentioned that I did some programs. I was in Next 36, and when I went to Asia, that was as a part of a program called the Cambridge Fellowship. You can ask me about those if you'd like. Add me on, any platform you like. And, a challenge that I'd pose to you guys is, I don't know if this is going to be possible within the structure this year, but maybe some people want to get together and do a quantum machine learning project on QMind. I really think that that would be way ahead of the game and almost exactly like what we had to do when we first did the very first machine learning project. It's all the same. You're learning something from scratch. You're relying on your own ability to decipher information and find good sources. And so it's a challenge, but it's probably worthwhile for those who can take it on. So that's everything I prepared. And for now, I'll stop sharing my screen. And if anyone has any questions, I'd be happy to answer them. I don't know if there's a chat. I actually can't see a chat. But if there isn't a chat, then no worries.
Hey Cooper.
Hey, Annie, how's it going?
Good. You mentioned like a couple, like we should start with like podcasts and YouTube's like channels and stuff. Like, what would you recommend to like initially delve into that?
Yeah, totally. I think that if you just search up, quantum computing on YouTube, you get a bunch of videos. Some of them are like nice animations. Some of them are interviews with people who work in the field. I think that's really to begin to understand like the concepts and the vocabulary. There's a lot of really crazy physics words when you get to the world of quantum computing, which, I tried to spare you from with this presentation. But understanding those words, just like the first time you heard backpropagation, it's important. And so you can really get those from those podcasts. And then once you kind of feel like you know the words, you can start playing around with programs. There are like completely like tutorials from start to finish that will take you a month or so. But at the end of that tutorial, like you'll be very knowledgeable about everything I talked about.
Awesome, thank you.
Yeah, no worries.
Hey Cooper, what do you think about Google's quote breakthrough? Was it a couple months ago? Or no, it was about a year ago, where they said they reached quantum supremacy, and then like, I think they were doing something about random number generation, and they said they did in, was it 200 seconds what would take a normal computer 10,000 years, but then IBM kind of stepped in and said, no, it actually would only take 2.5 days. What's your kind of perspective on that?
Yeah, that was interesting. I definitely am not like in the academic community by any stretch. I'm much closer to being in the Queen's community. But I think
Fair.
that I remember the people that I worked with, because the founders that I worked at that startup at, they understood that in a way Google had kind of set up a question that would be very easy for a quantum computer and intentionally very difficult for a classical computer. So it's almost like a very extreme example, like if you had been able to design the question that you knew the answer to. So
Okay.
that's what made it controversial. But I think that what made it, quantum supremacy is basically like the idea of this is the first time a quantum computer has like actually been able to operate on a problem faster than a classical computer. And these are supercomputers. These aren't laptops, so it is impressive. So I think it was a landmark, but I think people are waiting to see more legit problems being solved. Which they are. There are a lot of projects going on where quantum computers are being used to like optimize traffic flow. Quantum computers are being used to, as I said, like plan shipping and logistics routes. So I think we're going to see in the next few years quite a lot of actual tangible problems that people don't think are like contrived. So it's it was an interesting moment. It was a landmark moment, but I think that people had some quips about wanting things to not be so academic and like actually applicable.
Fair. Okay, thanks for that.
Yeah.
Alrighty. So, I mean, I guess if no one else has any other questions, thank you again, Cooper. It's always nice to hear from the original QMine man himself. He's kind of the reason QMine exists, and we're all here. So it's always nice to get a presentation from him, hear his thoughts. There are 2 more lectures happening from 4 to 4:30. There's an unsupervised learning lecture as well as a applications in finance for AI. Yeah, those are from 4 to 4:30 as well. If you haven't already, do submit your results for the hackathon. Those are due at 4. So we're getting pretty close to the deadline here. But yeah, thanks again, Cooper.
Yeah, my pleasure.